In this module, we look at the capacity of tension members. We will explore what common tension elements are. We will look at the capacity of tension members, the characteristic tensile strength of timber elements, and most importantly, the tension area. Tension members are most commonly found in buildings in trusses. And so trusses can be decorative or they could be buried deep within a structure. But in each case, a truss makes use of tension members and compression members to transmit loads. The capacity of tension members is given by this design equation. Again, the design loads for the strength limit state are evaluated and those are resolved into tension forces in the member that we're designing. That's our N star T, so that our tensile strength limit state force has to be exceeded by the tensile capacity of the member we're designing. The tensile capacity is given by this expression. And this expression looks a little bit like the bending capacity in that it's got a phi factor, K1, 4 and 6. It's got a different right-hand end where it's the tensile strength times the tensile area of the member. The phi factor, the K1 factor, the K4 factor and the K6 factor are evaluated exactly the same as for bending members. They all allow for service conditions and the module on the capacity of bending members gave the background on each of those elements. The tensile strength of timber is a little less than the bending strength of timber, and it's the same for all timber elements. The tensile strength is often dictated by characteristics that grow within the timber, such as knots. The tensile strength is different for hardwoods and softwoods of the same stress grade. And in each case, the tensile strength is a function of the size of the tension member. The larger the member is, the more probability there is of finding strength-reducing characteristics near the outside corners, and as a result, the tensile strength is a little less. Tensile strength of timber members can be found in Section H, Appendix H for sawn timber, Section 7 for glulam, for LVL from the manufacturer. The tensile area is the final piece of the tension capacity expression, and it's a function of how much fibre there is in the member. We look at the cross-sectional area to give us the gross section, but where we've drilled a hole through the member, we have removed some of the fibres, and so we have a reduced tensile area. So if we think about the way the load is applied into a tension area, if we've got a hole and we've put a bolt through that hole and now we're putting load on that member, we're transferring load into the member at the back of the connector. It has to find its way around that connector, and so the tensile area is the gross section minus the area we have removed for the hole, so that the tensile area does take account of holes in the cross-section. With nails, they don't actually remove material from the cross-section, they simply compress the fibres so that there is no need to reduce any of the cross-section for nails. Serviceability of tension members can be found using an elastic serviceability expression. However, it is rare that we get enough extension of a tension member to cause serviceability problems. So while we can evaluate the serviceability of tension members, it is rare that that actually limits the design. In summary, tension members are most common in trusses. They are usually designed for the strength limit state, and the critical element is the tensile area, which does have to remove, or which does account for the removal of some of the cross-section where we drill holes through the member. It is for bolt holes, but it could be for any holes in the section. So anywhere a hole is drilled through the section, we have to reduce the cross-section to account for the removal of material by that hole.